The thing I've managed, and actually the field managed to skip for a long time about this dopamine story, is the thing that I think, as those of you who are computer scientists know, is what RL is especially known for, is the ability to deal with a sort of more complicated set of decision tasks beyond bandit tasks, right? So, bandit tasks are sort of a terrible model of real-world decisions. Lots of real-world decisions, you don't just get a choice and then immediately get shocked for it or not and then move on to the next choice. Things like mazes or chess or football or graduate school, you make a bunch of choices and you get a bunch of rewards along the way, and they're interdependent in some way, and they have delayed consequences, and there's the famous credit assignment problem and so on. And a lot of what the full reinforcement learning machinery is about is optimizing behavior in that more complicated setting, right? And this, in principle, is an important part of even the dopamine story I've told you so far. It's just not. It hadn't got as much experimental attention. Something people have gotten a lot of interested in more recently. So, the idea, roughly speaking, and we'll talk about details in a bit. People have thought about Markov decision processes where you take, you're in some state, you take an action, you get a reward, and you go to a new state. And this happens cyclically, and you're trying to maximize, say, the total obtained reward in an episodic problem, or future discounted reward in an infinite horizon problem, where this expectation is, I have it written down, stochasticity and reward delivery and state transitions, right? It's a Markovian decision process. So that's the sort of a somewhat fuller reinforcement learning problem that is mainly the one that Rich and Andy are known for sort of posing and solving in some ways. This is a figure from Rich and Andy's book. Again, making the point that you have a reward in a state, you take some action and you get a new reward in a state, right? And the sort of classic reinforcement learning approaches all turn on what's known as Bellman's equation, and we'll unpack a simpler version of this later if you're not familiar with this, where Q, which is like the value function, the expected future reward associated with a state, some action in some state, depends on the current reward, and then recursively on the reward you're going to get in the future. And we'll come back to that depending on where you end up and so on. Okay, so for those of you who aren't as schooled in this, let's just go through that a little more slowly, although I said I wasn't going to spend a lot of time explaining reinforcement learning. So let's come back to a case without actions. I'm just trying to predict rewards, but I want to predict now the sum of rewards that will follow me from a state, and I'm being sloppy, avoiding expectations and so on, but I'm going to get reward at time t and t plus 1 and t plus 2, and I want to understand that. The idea of Bellman's equation is that I could write, recursively, I could write that, potentially infinite sum of rewards down as the sum of the next reward, R of t, plus the expected value of v of s of t plus 1. So v of s of t plus 1, the value of the rest of the rewards, if everything is in order and again an expectation, should be the rest of these rewards. This v and this one are the same except for this one reward at the tip of it. And writing out that expectation a little more carefully, the value of the reward, the value expected future reward at state s of t is the reward at state t plus the expectation over all the states you might end up in, give you start at t, the value of that one, right? So this is an objective function. This is the thing I want to optimize or to learn. I want to make choices so that I earn the most expected future reward possible. And this is a little harder than the one-step reward, like in a bandit, obviously. And temporal difference learning basically can be thought of as applying sort of two ideas to learn these values, sampling and bootstrapping, right? So I can, for this expectation, I can be in some state and observe what the next state is and what the next reward is, and I can use the observation of this s of t plus 1 as a sample of this full expectation over the future expected state distribution, conditional on where I am. And bootstrapping, that is, I might not yet know for sure what's the expected value of this future state sequence from S of t plus 1, but I can use my current value, my current beliefs about that value as a stand-in for that, and learn on that basis. So it's a little bit surreal trying to explain temporal difference learning in Rich and Andy's presence, so I apologize if I faint. But anyway, I'll keep going. So the idea then, you sample a bootstrap, and I feel like I should invite them up. Like if I were playing a Beatles song and, okay, sorry. Then you're going to use this error-driven dynamics again to sort of average over these samples so that you can, do a sort of gradient descent on this expectation. And you have a new prediction error now. It looks like the old one, but it's not just reward, the expected minus the reward you got, or the reward you predicted minus the reward you got. It's also got, because you're trying to predict not just the current reward, but the future rewards, R plus V minus V, right? So we've added a sort of extra term to our prediction error, but it looks awfully the same, but it magically lets us learn not just the current reward, but the sum of all future rewards through the magic of Bellman's equation. Okay, again, what this says is we can learn to predict the cumulative future rewards from some state. Again, the reason for this is so we can solve multi-step decision problems using what I predict at time t plus 1 as a sort of stand-in for this whole future set of rewards. So I don't have to wait to the end of the chess game to see if I win or lose to compute this sum. I can immediately compute at time t plus 1 where I think I'm going, and I can use that to learn a little bit about where I came from, right? And this is called temporal difference learning because another way of kind of debracketing this, I've sort of shown this as what I expected minus what I got, but you could also consider this piece. So if the rewards are 0, then this prediction error is just the difference between what you're expecting at one time step and what you're expecting at the next time step, which is to say if everything is working out and I'm not getting rewards, in a game like football, scoring points is very rare, but I'm constantly changing field position. If things are learned well, then expectation, those two values should be the same, right? And if I have an unexpected increase, if V goes up, if this temporal difference is positive, then things got better, and I've got have positive prediction, or I underpredicted at time t, and if it went down, then things got worse. But these are not these are changes in your expectations. They're not rewards themselves. So, for instance, if someone calls you up and tells you won the lottery, then that's positive prediction error, not because they gave you food or water and the actual reward. It's because your expectation of future reward has changed for the better, right? And that's a positive prediction error. If you're at the bar and the server takes away your drink, like when you've still got a couple sips left in it, like the thing that I hate, right? And you have that like angry reaction, that's negative prediction error, right? It's not like they spilled coffee on you, which is negative reward. It's like your expectation of future reward has gone down by 2 sips of beer, right? And that's a negative prediction error. So it's a change in expectation. And the secret of temporal difference learning is accounting for changes in expectation and treating those as though they were rewards, right? Having them drive prediction error and drive learning, okay? So that's like the two-sentence version, two-slide version of what temporal difference learning is, and that brings us back to dopamine neurons, right? So what we talked about before was the sort of Rescorla-Wagner account of the responses to rewards in this kind of episodic case where you tell animals that there's a reward coming and then you give it to them. And we didn't really talk about why there's these anticipatory responses. And the idea is they're also prediction errors, right? Just in this more general case, what happens if you're sitting in the dark and not really expecting anything because these events are rare, I'm sort of expecting 0, and all of a sudden a light comes on that tells me I'm getting juice in a second, then I have a positive prediction error, which is something like V of t plus 1 minus 0, right? So I have, so importantly, you can understand all these responses, and this was sort of the genius of these original computational papers. Schultz had written about these responses in different papers as being different things, but they're all instances of prediction error once you understand what prediction, once you define prediction error generally enough, right? So these are cases in which your future reward expectancy increases even though you're not getting a primary reward, and that induces a prediction error, and it can drive learning. If there had been some other event previous to this that predicted this, you would learn that you underpredicted, and then that would support that kind of transfer even further back over a chain of stimuli, right? So that's the idea, and that obviously generalizes to sequential decision tasks as well. It also, for the same reason, I hope it's obvious now, explains second-order conditioning, which I mentioned a long time ago is something that Rescorla-Wagner never properly got. As I said, TD is really all a theory about how changes in your expectancy are, drive learning. And so locally, I see a light and it leads to a bell, and that bell predicts steak, then I have some positive prediction error and I learn about the light. And so that's sort of, in a nutshell, behaviorally, this effect is exactly what this dynamics, this sort of learning rule is supposed to make happen because of this bootstrapping, right? Because I'm using my prediction in light of the bell to update the light, okay? Okay, so, and this brings us to choices in sequential decision tasks. And so this also brings us to the anecdote part of the presentation. So let's do that. So, okay, so this funny greater than sign is economist notation for I prefer X to Y. So I like tsutu nigiri better than kind of a flat hamburger. And so in a kind of sequential setting, I like Nobu, which is a great sushi restaurant in New York, better than McDonald's, and extending it further back, this makes predictions about which subway I would prefer to get on to go to dinner, and so on. All in virtue of my preference over the rewards, right? And that was the case until I woke up and read the newspaper one day, and the New York Times had actually snuck out of a bunch of the finest sushi restaurants in Manhattan and Brooklyn with tuna. And sent it to a lab, and it was all incredibly poisonous, right? It was full of mercury, just really alarming amounts. And there's this sort of tables of mercury amounts and fancy restaurants, and like these weird figures where like it plot the amount of, let's see, income against blood mercury levels in Manhattan residents, and this is because income is sort of a proxy variable for how much sushi you eat, and just all very scary, right? And of course, so now I prefer the hamburger, having read this. This is scary stuff. And so this leads to kind of an experiment, which is you put me back out on the street and ask me what train am I going to get on, or where am I going to go to dinner? And obviously the answer is if I don't want the sushi, I shouldn't go to Nobu. I should now prefer McDonald's. But of course, that's only in virtue of the sort of sequential relationship between actions and outcomes here, sort of state transition matrix in kind of RL terms, right? That if I go here, I'm going to end up getting this reward and this outcome. Whether I make the correct choice here depends a lot on how I learn. So it could be that I get on the, I just get on the, I go to the place I always like to go for dinner, I get there and I realize, oh my God, I got sushi, that's a negative prediction error, and I don't go there the next time. That's at least possible. One way to think about that a little more carefully is to kind of write down a kind of mock version of Bellman's equation here, which is sort of simplified for simplicity, where we think about the expected value of different actions, like going to different restaurants or getting on different subways, as arising from some kind of an expectation, let's say in this case, over sort of the ultimate outcome that I'm going to get, like, for sushi or hamburgers, and the value, my value, or you might write that as R for those outcomes, right? And so what this says is, I want to choose the action that maximizes my expected value, an expectation over the sort of menus of the restaurant. So I have the how much do I like the different foods, and what food am I going to get in different places, and that's a sort of simple version of this. And the key thing to note is that because this is an equal sign, I could really legitimately work on both sides of this equal sign if I want to solve this problem by trial and error, right? And this is familiar to people in reinforcement learning as the model-based and model-free distinction, right? So again, part of the innovation of Rich and Andy was that they showed that there are these model-free algorithms, even the sequential case, and we just saw them, right, for learning about expected future values without having to keep track of maps of what actions lead to which outcomes and which subways lead where and stuff. And of course, and you can just do this all by bootstrapping and sampling, and what you get at the end is a table of, for each action I could take, how much reward have I gotten for doing that. But if I did that, and that's the dopamine story, right? That is the story that people have in mind when they think of dopamine. if that's the way I'm working, then I should actually make a mistake here. I should actually nothing in learning about the horrors of sushi in Manhattan tells me anything about getting on a train, right? There's no connection by design here between a table of numbers about trains and sushi, right? I've escaped that by escaping modeling. And so that theory predicts, the dopamine account of my behavior predicts that I should get on the wrong train and go to Nobu and get a negative prediction error when I realize I don't want the sushi. Whereas, of course, the kind of older family of approaches to reinforcement learning that prevailed, in a sense, prior and still is worked on to the temporal difference learning kind of revolution is called model-based. And the idea there is you can learn all the kind of one-step or different variations, say the one-step contingencies of the task or these sort of maps of menus and so on. And at decision time, perhaps, stand there on the street and compute, if I got on this train, I'll go here and I'll get that, and that's good. If I get on this train, I'll go here and get that, and that's bad, and compute your decision variables online. And so these are two different kind of legitimate approaches, but depending on the particular information you get, they might make different choices at particular times. They might take a different path to asymptote, as it were. Okay. And again, this is a familiar distinction in reinforcement learning, so I may have just bored you all, depending on who you are. This experiment caricatured here has been done a lot. It has got a lot of interest in a certain kind of community in behavioral psychology, where it's been done with rats. So classic experiment. This really goes to Tony Dickinson kind of invented this, and it's based on logic that kind of goes back to Tolman, the cognitive revolution. What the idea is that you have a rat lever pressing for food, let's say, like some particular cheese, and then you devalue the food. So the rat lever presses, gets food, learns that this lever gives you food. You then poison the rat, pair that with cheese. Rats and actually people are also very good at food aversion learning. If you learn that some food has made you sick or has been paired with illness, you'll stay away from it. And rats have a very strong form of this, kind of a single shot learning. So rats will develop a very strong aversion to the food. They won't want it. You give it to them, they won't eat it. And then you can put them back in the cage and ask, will they lever press for food, right? Will they work for this food they don't want, okay? And again, the prediction of kind of model-free reinforcement learning and more generally of this kind of dopamine story of decision-making is that animals will make a mistake here. They'll like work, at least until they start getting the food and realize they don't want it, they'll work perfectly well for food they don't want. So this control procedure of this experiment is slightly complicated, but let me just mention, you could imagine having another group who devalue a different food or who don't have stage 2 at all. And what you want to ask is, do rats work harder for the food they want compared to the food they don't want, okay? But you're going to do all of this not giving them the food in stage 3. Because we'd like to see that what we want to do with this experiment is ask, do the animals, in making the decision whether to work and lever press, are they contemplating the identity of the outcome, right? Are they contemplating which food they're going to get for it in this sort of model-based way, or are they just lever pressing according to the sort of stored policy or Q value, right? And so if you don't give them feedback, you can watch, them extinguish. They'll stop lever pressing over time when they don't get the food. They get negative prediction error also. But the point is, the animals who don't want the food in the first place, if they're model-based, will stop lever pressing faster. They won't lever press in the first place. Right? So there's sort of a comparison. Okay, that's the logic. And the result is mixed. The answer is animals sometimes make this mistake and sometimes don't, depending on circumstances. So these are data from Peter Holland. And what you see, if animals were sort of moderately trained in this first phase to lever press for food, then they are outcome sensitive. So they'll lever press less for the food that was devalued than valued. And again, because of the control procedure here, this demonstrates that the identity of the food kind of goes into the decision to lever press because they're not getting the food during this phase. So this difference implies that whether or not they lever press depends on them thinking about which food they're going to get and if they want it, right? So this kind of falsifies the sort of simple reinforcement learning kind of model-free account that just says they've stored predictions about reward or a policy. However, psychologists refer to this as goal-directed behavior, where the goal is the particular food. if you overtrain the animals in the first phase, like 20 rather than say 3 sessions of lever pressing here, then what you find is the animals will just happily lever press as much for the food they want as for food they don't want. This is referred to as habitual, and this is exactly the sort of mistake that I said that these kind of simple model-free reinforcement learning algorithms predict, right? So indeed, animals will really work for food they don't want sometimes. This is called habitual because it's supposed to be a kind of laboratory model of something that we all experience, which is that with repetition, our actions seem to become sort of automatized or something. So you get on the elevator and you usually go to the lobby, but every once in a while you have to go to the basement to do your laundry, and you press the lobby anyway, and then you realize that you press the basement, right? Or you turn one way to go to work, but some other way when you're going somewhere else at a stoplight. So this is thought to be a sort of animal version of that, right? Okay. Okay, so it's also, so this appears to be sort of 2 modes of behavior, one of which is pretty well associated with the kind of computational neural circuitry we've talked about so far, one of which is a little more mysterious. It also appears from lesion studies that these 2 networks are distinct. So for instance, different areas of striatum, so dorsolateral and dorsomedial, also known as caudate and putamen, different cortical striatal networks, if you burn them out in the rat and then have them lever press in this way, you can observe that rats who seem to know how to lever press perfectly well are doing so either on the basis of goal-directed behavior or habitual behavior, when normal rats would do it in a different way. So this is a case, and this kind of double dissociation suggests that there are really separate brain networks supporting these 2 kinds of behavior. So for instance, here we have animals who are overtrained, and so normally they'd be habitual. They're lever pressing for food, but you do this evaluation and they still lever press for the food just as much. That's this habitual case. That's the control animals. But if you burn out the dorsolateral striatum, one of the targets of these dopamine neurons, then the animals are lever pressing fine. But when you devalue them, you see that they reverse lever pressing just like animals who were undertrained. So as though their behavior all along was governed by this sort of goal-directed system instead of the habitual system. They're missing the habitual system. So this kind of thing, and they have inactivations that are temporary and stuff as well, suggests that these 2 systems operate sort of in parallel, if you can think of them as 2 systems. Okay, so what have I said? I've said that the same action, that is lever pressing, can arise from 2 systems that are behaviorally and neural distinct, that can be distinguished with this devaluation test, but otherwise you have to be cautious in telling which one you think you have. So overtrained lever pressing is devaluation insensitive. That's called habitual, and it's what's predicted by temporal difference learning, right, and by model-free reinforcement learning, and basically closely associated with this whole story I've been telling you about dopamine, so we have sort of a theory of habits. But moderately training lever pressing is devaluation sensitive, called goal-directed, demonstrates that animals are sort of paying attention to outcomes internally when deciding what to do. Maybe this is non-dopaminergic. This is not completely clear. And these seem to be 2 distinct action systems.
So
yeah.
Can I ask a quick question?
Yeah,
so
sure.
Whether it's goal-directed or habitual behavior, is that dependent on how long the animal has trained? So whether a model has even been learned at this point in time, right? Because the models have to come from somewhere too.
Yeah, so you might think, so people often have the intuition that it takes a while to get a model, and before that you should be model free. And that could very well be true, but we're in a regime, presumably, it's a very simple model, right? It's a 2-step thing. It's like I lever press, I get food, I like it. So we're sort of past that. And then the question is, if you train even more, do you revert to a habitual, a model-free setting? And the intuition, let me just preview it, is that it would be kind of crazy, if you think about when data are scarce, it's worth engaging in Bellman sweeps or planning of some sort to wring whatever you can out of the data you have. And by the 20th day where you make the same choice over and over again to the same outcome, you might as well just use the Q value you've got on hand, right, or the policy, right? And it's just not worth, you can make, in general, deliberating, in a sense, recomputing something that's been, stable, right? That's the idea. But you're right, that there might be stuff going on in the very low training regime as well that hasn't been uncovered. Okay. So I hope it's obvious because I said this out beforehand, but just to be clear, I mentioned why model free learning, can't adapt to changes in reward, devaluation, and model-based learning. If what I did was store, this is a diagram of a slightly different task, but if what I did was store future outcomes and their rewards separately and plugged those in at decision time to Bellman's equation or a utility equation to decide what to do, and I call that kind of model-based reinforcement learning, then that, in a sense, might provide a characterization or a theory of what animals are doing in the regime where they seem to know about outcome values, right? And there's spatial versions of this where the model can be thought of as like a spatial map or something, and otherwise similar stories about overtraining and so on. Okay, so we might think of this trade-off between habitual and goal-directed behavior as computationally arising from a kind of trade-off between model-based and model-free learning. And so this brings us to and I'm actually not going to dwell on this today, some work we've done, and others have now worked on, that hopes to shed light on why the brain has multiple decision-making systems. Why is it that you have, say, a goal-directed habitual system or a model-based model-free decision-making system? It seems duplicate, it seems like it compounds the problem of choosing actions rather than solves it, because now you got to choose between the controllers and not just choose what to do, right? So that seems, at first glance, to be a problem, but the idea is that they might be kind of useful. They're different approximations to, in a sense, different algorithmic approximations to the full, intractable, Bayes optimal solution to the reinforcement learning problem, which is to, induce a posterior distribution over all possible MDPs and solve each of them and, average or whatever. Certainty equivalent model-based reinforcement learning, let's say, and some kind of simple model-free reinforcement learning might be differentially appropriate in different circumstances depending on a lot of aspects. One such aspect is how much experience you have. So as I mentioned, if you don't have a lot of data, it may really be worth doing a lot of pre-computation to try to figure out what to do. And once you've learned a lot, Q-learning is going to do just fine, right? And so you can sort of derive from this kind of idea a kind of meta decision theory, in a sense, or an account, at least qualitatively, of why, under what circumstances the brain should adopt each of these strategies. And you can think of it, it's a little bit like self-control or control. It's a theory of, when should you deliberate and when should you act, right? And it sort of weighs the costs and benefits of deliberation against the cost being, time and calories, perhaps, against perhaps making you make a better choice, right? And I'm going to skip a couple of things and talk a little bit about. Well, maybe I'll say one thing. A number of people. This is an idea in the context of Markov decision processes and reinforcement learning, but in other areas of kind of cognitive control and executive control, like costly mental effort or allocating working memory and stuff, people are kind of interested in similar rational accounts, like how should you allocate working memory, when should you be willing to engage in difficult mental effort, like unscrambling anagrams in an experiment or something. These sort of quasi self-control, executive control issues. There have been a lot of these sort of manifestos recently, kind of arguing that we should take a rational kind of cost-benefit approach to these things. This is probably the one at this point that's kind of best worked out, but we're sort of hoping that this kind of thing will apply more broadly to these other kind of more frankly self-control kind of situations, insofar as they also have this kind of trade-off between sort of thinking and acting, is one way to say it. Okay. Let me say a few more things. People have also, we and others have looked at, and people playing, multi-step MDPs to try and look at this distinction between model-based and model-free learning now in humans, and people are now doing this in animals too. So this sort of one of the simplest possible versions of this We don't like to do reward evaluation. Poisoning people and stuff is no fun, so we've looked to other kinds of experiments. One thing we've done is a sort of multi-step bandit task where people choose between two, say, slot machines, here represented by different Tibetan characters, and that induces a state transition. So instead of giving you rewards, it leads you to another state. So this one leads you, say, to the pink ones. Most of the time, those give you money. Some fraction of time, so these are like a bandit problem. This is like a meta bandit problem. So this one leads you to, primarily to a different set of choices. So every trial I choose a green one and then a pink or a blue one, and then I get reward or not. And importantly, this coupling from top level to bottom level states is stochastic. So 70% of the time, I go from this choice to here, but sometimes it'll lead me to the blue ones anomalously. Okay. Now, the reason this is interesting is we can look at kind of trial by, so we keep these rewards again slowly changing. So again, it's a kind of non-stationary bandit task, as it were. And we'd like to understand how people adjust their top level choices in response to the sort of bottom level feedback, because model-based and model-free approaches make different predictions about that, kind of analogous to the reward evaluation case, but happening on every trial. So here's one sort of indication why that is. So if, say I chose this guy, and I got this sort of rare transition following that, and then I chose this guy and got rewarded, then at the margin, what should that do to my preference at the top level in the next trial? So if I were doing what's known as TD1, right, for the reinforcement learning fans, if I'm doing a sort of simple kind of sample-based reinforcement learning where I choose this, I get rewarded for it, I strengthen the value of this one, then on the next trial, I should be more likely to choose this guy, than if I had not got rewarded for this, let's say. On the other hand, right, that's a little bit crazy. What I really know, what I really learned from this trial, if I'm doing a model-based kind of thing and evaluating these options in terms of their consequences, is that this box is better than I thought. And so what that means is I should be more likely to actually choose this guy and not this guy, because that's the one that more often takes me there. Right? So if I'm doing model-based reinforcement learning, then this choice, actually its value increases through the increase, because this value depends on the value of this one. Right? And again, these two things asymptotically lead to the same optimal actions, optimal policy, but in terms of their trial-by-trial adjustments, they go in opposite directions on this kind of a trial. Okay, so this is one way we've tried to look at this distinction in people. So another way of saying what I just said is if we compare sort of TD1 to model-based planning, if we plot, it's kind of in the spirit of these regression analyses I showed you before, if we plot the probability of making the same choice on trial T I made on trial T minus 1, like choosing this green guy again, as a function of whether I got reward or not on trial T minus 1, and whether or not that happened after a common transition like to pink or a rare transition like to blue, then TD1, what I just finished saying, model-free reinforcement learning doesn't care about common versus rare. It just cares about whether I got rewarded or not. So you have a sort of main effect of reward versus non-reward. If I did the same thing for model-based planning, so because of the symmetry of the task, what I also just got finished saying is that non-reward, or a rare transition kind of reverses the meaning of reward, right? It actually applies to the other state. And so you should see this kind of crossover interaction where reward means one thing after a common transition and the other thing after a rare transition. So sort of a simple way of visualizing data to see if we can see the distinction. Of course, what we hope is that we can see both of these things in people because we think they're both going on in the brain, and then we can try to push around, when and under what circumstances that is. And the short of answer is that we do see both. So this is individual subjects data. So some people look completely model-free. They just have a kind of main effect of reward. Some people look almost completely model-based. They really reverse the meaning of reward following a rare transition. And a lot of people are kind of somewhere in between, which you might think of as a kind of weighted average of this and this, like either across trials or within trials. That's hard to tell. This is average over trials, obviously. They're combining those two sorts of mechanisms. Yeah.
Just a quick question. What about other methods like TD learning with experience replay? Doesn't that get... because that would have...
Yeah, that's something I'm going to actually come back to. Yeah, so there's a sort of mechanism question of what this is showing is that some kind of Bellman backup happened, other than. So yes, experience replay, if you do enough of it in between trials, will give you a model-based like effect here. So that's a sort of process level question of how is this happening. I have a whole section where we'll talk about that. It's a good question. For now, let's just imagine this is the possibility that's just planning at decision time. Yeah.
Do you have a hypothesis about why some people learn model-based, other people learn according to model-free reinforcement learning, and how we might perhaps shift people who are model-free to model-based or vice versa?
It's a good question. We'd like to get money to study that. In seriousness, people think about model-free drugs affecting dopamine and model-free reinforcement learning being kind of habits and compulsion. Like there's a sort of strong emphasis of people thinking that one of the problems with disorders of compulsion, like drug abuse, is cause and effect isn't completely clear, right? But they're basically causing some kind of imbalance and kind of behavior that's driven by model-free sort of policies that are learned that aren't appropriate, and that the subject actually knows better, but their behavior is driven and kind of imbalanced by this kind of habit system. It's one example of that might be caused by drugs knocking out your prefrontal cortex or something. I think that's what Nora Volkow thinks. It could also be that some people, for whatever reason, are more habit-driven, and some people are more deliberative. And there could be other reasons, so IQ and age and so on all co-vary with this. So people get more, as their brain ages, they get more habitual, for instance. So there's a long kind of individual story here, but the point I want to make just today is that these two patterns seem to be visible in people's behavior in different proportions. Yeah.
Maybe I'll speak up real quick. Can you push people one way or the other by the instructions you're giving?
I'm trying to think if we've done it with instructions. We've done it with, if you just tell them, people can follow instructions, right? So if you tell them, here's what I want you to do. I want you to switch whenever you have a rare transition and so on, then sure, they'll do that.
Or if you tell them there is an underlying structure.
We do tell them that. So we actually give them fairly careful instructions about the nature of this. We actually even tell them in some versions the transition matrix. So they really know the model, in a sense. But that doesn't necessarily govern their behavior, right? Yeah.
Have people looked at animals on this kind of task, like rats or something like that?
People are just now. So the thing about human neuroscience is it's faster. So we've been able to iterate through a bunch of versions of this and figure out how to do it. And it's now animal people are picking it up. There might be some posters here. I don't know. Last year there were a couple posters from the rat groups doing this. I'm not sure. Carlos Brody's group is doing this, and Rui Costa's group is doing something like this. So yeah, there are animal versions of this ongoing now. Okay. So you can push people around in subtler ways, which I think let me show you one example. There's more. Anyway, in the net, what you see is on average across subjects now, you have both the pattern that we think of as model-free and the pattern that we think of as model-based in sort of roughly equal proportions in these sort of circumstances. And let's go then to this question of this thing we're talking about as model-based. How is it really being computed? So this experience replay question is one possibility. So let me just say, so in this experiment and in many others, like the reward devaluation study and various kind of route replanning experiments in spatial domains and stuff with shortcuts or barriers, animals and people seem to be able to kind of do what looks like model-based planning, that is, using knowledge about the transition matrix of the world and the rewards to sort of recompute a policy. The assumption that I think people have had in mind, certainly we've had in mind, and I think people going back to psychologists like Tolman have had in mind, is that there's some kind of dynamic programming at decision time that's going on, right? That I sit there at the top of the game and I think, well, if I go this way, I'll get that, and I'll get, there's actually kind of forward planning at decision time. Of course, that doesn't have to be true. What I take to be kind of one of the major points, again, that Rich and Andy have made in various ways, like in their book, is that variations on these same kind of Bellman backup operations in sort of different orders at different times, kind of amount to different ways of getting to the same answer, right? So one example that the gentleman already mentioned is experience replay, like in Dinah, right? If in between trials, or after I got poisoned food in the case of the rat, I go to sleep or spend some time dreaming or replaying previous events and pushing those rewards through the transition matrix more generally, I should be able to replan and derive what looks like model-based planning. It doesn't have to be actually triggered by making the next choice. So let's see what we know about this, and the answer is not a lot. So we're just at the point of being able to behaviorally really measure these things with enough power that we can ask questions about mechanism, and this is where the animal stuff is going to come in. But one very suggestive set of data comes from rodent navigation. So Dave Reddish has been, and David Foster have been the two people that have really pushed this idea. So you may or may not know that neurons in the hippocampus, someone just won the Nobel Prize for this. So the hippocampus is an area of the brain. In rodents, the hippocampus has neurons that fire at particular locations of space. And so you can read off from hippocampal activity where the animal thinks he is, except that sometimes that representation seems to run ahead of the animal. So this is an example, sort of anecdote from David Reddish, but there's, it's just an anecdote, but there's real data here. This is a sort of T-maze experiment where the animal has to decide whether to turn left or right. He's standing here at the junction, he pauses, he's not moving, but there's this rapid oscillation in his in the representation of space in his brain that suggests that is flittering back and forth across the two choices, as though there's a sort of some kind of anticipatory model evaluation going on. Perhaps that's certainly how David interprets it. So this sort of might be a substrate for, in a sense, simulating future transitions, so you could add up the rewards or something along them and decide what to do. Right? That's not really demonstrated here. In part because they don't really isolate whether behavior is model-based or not. There's not much behavior going on in these experiments. Here's another one. This is from David Foster. This is an open field experiment now. The rat just runs around and forages for reward. But you see these very dramatic events where the animals come along here, the representation runs ahead of him, and then the animal goes where the representation went, more often than not. It's really quite dramatic. I sat with David and watched videos of this for a long time. It's really quite something. And again, this could be planning. It could be not, because there's no real understanding of the behavior here. The animal's just wandering around. But it certainly seems like his hippocampus knows where he's going to go before he goes there. Okay? So this has been taken as evidence for kind of model-based planning in people, or in rats, rather. We've looked at a couple related things in people. So one is that we crossed this task I just talked to you about with a dual task manipulation. So we thought that if we could interfere with people's kind of working memory capacity, there's sort of a classic idea from cognitive psychology, then we could we might be able to wipe out deliberation without affecting kind of model free learning if that's more implicit or automatic. And that's indeed what we saw. So when people are doing a sort of under the single task conditions, this replicated our original study, but on about a third of trials, people had to remember a letter and a number over the course of the trial. They're shown it before they get into the first stage, and then they have to answer a question about it at the end. And when they do that, on those trials, they behave as though they're not like random, they're still behaving in a structured way, but the model-based part of the behavior is sort of knocked out, and all that's left is this main effector where this model-free reinforcement learning. So we can sort of, this sort of within subject on neighboring trials, we can interfere with what appears to be this planning process at decision time and drive people between model-based and model-free. We can also, I'm not going to go into details on this, we can use faces and houses, we can decode, in this case, body parts and places. So when people are sitting up here deciding what to do in one of these multi-step MDPs, we can use decoding an fMRI to ask, are they thinking about this state or that state? And the extent to which that predicts their choices, the extent to which we can do that across subjects predicts to what extent they look model-based or model-free behaviorally. So more model-based people, you could read out from their brains what states they're thinking about, where they're thinking of going, and more model-free people you can. However, so those are two sort of lines of evidence that perspective activation might, oh, good. Yeah.
One quick question about again, kind of pushing people towards model-free or model-based. Similar to that task with the interfering task, if you have a distractor task going on, like having to remember a stream of numbers the entire time of the test, would you see a similar push towards more model-free methods?
Yeah, so that's actually, we did that in the same paper. There's a
Okay.
between subject version of that, where half the subjects had to do both at the same time and half the subjects had to
So
switch
like your
back and
mental
forth.
resources are taken up by something else, and
Yeah.
then you become more model-free.
So those people look like this the whole time.
Okay.
And this is the within subject. Actually, the graphs look the same. I could very well have the wrong graphs here, but I think this is the within subject version.
And then relatedly, has there been any studies of kind of the amount of time you give the animal, the subject, whichever, to learn? Because Dinah style thing is suggestive that it's going on all the time in little bits, and a planning thing is all front loaded at the beginning.
Yeah. So
Like, force
let
the
me.
decision faster?
I'll get to that in just a second. I have an
Okay.
example. I don't have the data, but I'll talk about that.
Great,
Yeah.
thanks.
There is a study. Good. So that's the high side. There seemed to be some evidence that stuff is going on in decision time that's perspective and is related to model-based learning. However, there's a bunch of other weird data that are more consistent with other kinds of things that are happening not at decision time that are driving this kind of seemingly model-based learning. So for instance, I mentioned that these place cells in hippocampus are associated with these kind of forward activations of places the animal's going to go, but they also have this kind of replay. So, when animals are asleep or when they're awake but somewhere else, you see these events that seem to correspond to, so this is an experiment that Lauren Frank did where a rat ran around in this maze with this particular funny 3-arm structure, and this is a series of place cells that can light up along this particular trajectory, and they go off when the animal's standing around in this box where these place cells don't live. So you have kind of remote replay of experiences trajectories the animal took in other places, both when they're awake and when they're asleep. So that looks a lot like Dinah. That is replay of experiences, driving update and helping you integrate them and solve these sort of problems that if I teach you one thing at one time and another thing at another time, then model-free learning doesn't put them together. So that's one example that might be true. There's also really weird things, again, in this rat hippocampal domain, like when the animal gets to reward, it often rewinds the cells and plays back the stuff that just happened. So the animal's sitting there eating reward, and it plays back the trajectory he took backwards, or even it kind of rewinds to the choice point and goes the other way. And so it looks as though it's kind of driving around the transition matrix, updating stuff along a trace or something, right? Or even also constructively, like along ways you didn't take. So there's really interesting dynamics here that are way more than just anticipatory, and could drive all kinds of interesting kind of learning schemes. And this recent paper by David Foster in particular, I haven't completely managed to make sense of, but there's lots of really interesting stuff going on there that could use some careful thinking. Moreover, and this is coming to your question, this is another 3-phase experiment, which is structured a lot like reward evaluation. So people learn, it's faces and body parts again, and scenes. They're associated with fractals, and then they learn the fractals are associated with rewards, and then they choose between some of the fractals and some aren't. They choose between the fractals. So this is another kind of reevaluation experiment where in order to, a model-free system can't really solve this problem. In order to make the correct decision here that I prefer this scene to this scene, I need to kind of integrate this reward experience with this association. So there's a lot of work on this kind of task. So Elliot Wimmer and Dr. Shahami and also Zeb Nelson, I think I saw back there, have both done this task with human brain imaging and decoding and shown that what predicts whether or not people succeed here, so again, there's individual differences, is not stuff that's going on in their brain at decision time. It's stuff that's going on in their brain at reward time, but in this retraining phase. So in particular, if I show you this and scenes light up, it's as though this activates the scene a little bit like that kind of rewinding activation in the rat. That gets paired with the reward. That's what predicts whether you solve this task in this particular setting. So that seems like a direct evidence for a different scheme, which is not really exactly Dinah either, but it's something, a kind of associative, kind of replay, associative learning mechanism. And then finally, in another of these revaluation tasks, and this is directly pursuant to your question, Sam Gershman recently published an experiment in which, in a number of different ways, he does phases like these two things, and then he rests, right? And depending on how long the rest is, or whether they have to do something else during the rest that's distracting or not, it changes the extent to which people solve this task, which really looks like you're messing around with some kind of replay. So here it's happening during the acquisition, during the learning of the new information, and in this experiment it's also shown that something's happening after. There's some problems with the controls in this study, so I wouldn't take it to the bank yet, but it's a kind of exciting idea anyway. It's a Journal of Experimental Psychology, JPG. So altogether then, I think, this kind of integration that people have been using, including ourselves, to support model-based planning is probably itself heterogeneous, right? So there seems to be some in the moment planning where you're thinking ahead about the consequences of reactions, but there's also kind of various sorts of replay and kind of associations that are formed non-locally when you learn stuff that's behaviorally giving kind of similar effects. And so then the real questions, again, come to this kind of prioritization or scheduling thing. What should you replay? When should you replay? What should you associate when? These sort of control problems, I think, are of real interest, and again, kind of relate to these bigger picture self-control problems that I was talking about. And in principle, there's a rational solution there, and I think it would be very interesting to understand better how the brain does these kind of prioritization kinds of questions when it plans in the moment, when it plans ahead of time, when it doesn't do either. Is that rational? Is that a cost-benefit trade-off? There's also, I should mention, other sorts of kind of pre-computation and caching that kind of don't fit well into the scheme I just gave of replay and preplay and so on, like the successor representation, where you cache long-run future state trajectories or end-step future state trajectory models. So there's a poster showing some evidence of that as well in people. So there's a little bit of everything, I think. I think it's a pretty interesting area. Okay. Wow, 3 hours. Good. So I have one more kind of grab all of just sort of directing your attention at some other things that I think are interesting to sort of finish up some other areas that have been of more current interest or that help to enrich this story, and where neuroscience and psychology have been drawing a lot on the examples, consuming examples from RL. Okay, so coming back to this figure of Rich and Andy's, and actually Andy often makes this point, the model underlying, this box is environment, right? And the environment's giving you the state and the reward, but of course the state is really partly in your head, right? So it includes things like what your motivations are, whether you're hungry or not, and whether you're tired or not, and what you've got in your working memory. And so what I'd like to talk about finally is these three symbols, which have a sort of clear meaning in the computational literature, state, action, and reward. I've been sort of fudging on their relationship to the situation that animals find themselves in, right? Like, what are these really? Can we be more realistic about what rewards are, what states are, and what actions are? Okay, so and I'm just going to sort of point in some directions about this, and then call it a day. But these are all abstractions, and we'd like to know how they really are. So let's start with reward. And actually, I think we've already covered this. So this is actually the thing that I think, in a way, the TD story has the strongest account of, because TD itself, as I tried to stress before, is already a really deep theory of what rewards are, right? Because they're not just this, it's seeded with these primary rewards. Those are something, presumably your body knows about, that fat is good, or calories are good, or sex is good, but then it just constructs this value function, which is all about, what other things are predictive of that. And so it sort of bootstraps, particular, perhaps, I know that calories are good, but then I learned that sweet taste predict calories or whatever. This whole story is a story of the construction of reward and the construction of value. And so I think that's actually a pretty rich story, and I wouldn't have much more to say about it, really. However, as we already mentioned, there's this sort of problem of punishment and how the brain deals with punishments and avoidance and so on. And I think I won't. I mentioned that dopamine neurons who look like, say, they don't like punishments, these air puffs to the eye, and the dopamine neurons that look like they like them as well as they like rewards, and they're in different places in the brain. they're anatomically separate. So it's still kind of a mess as to what's really going on here. And that's an important issue for future work. Okay, action. So what are actions? So we started with this idea of choice between bandits, right? And I already said this is just an awful model of biological action choice. So not just because actions are sequentially dependent, which is the other main strength of reinforcement learning models that I've tried to stress, but also because actions in the real world, it's not like you have a set of 3 alternatives and you choose between them. They're continuous, like trajectories. They're high dimensional because your body has a bunch of muscles in it. They're structured hierarchically in various ways, and this last thing is the thing I want to focus on. There's gotten a lot of interest in RL, obviously. So, for instance, again, all the people who invented this idea are here in the audience, but there are a number of different versions of hierarchical reinforcement learning ideas where you can construct kind of higher level actions out of either sequences of lower level actions or kind of higher level goals that induce kind of policies over lower level actions or some variant on this. And the idea is this allows you the ability to kind of view the decision-making problem from greater or lesser levels of abstraction. And that really the point I want to make about this is, and Matt Botvinnik has been the one in my community who's worked the hardest on this, and Yael Niv. This really is an idea about how to make this action A more than a list of the 3 bandits in the world right now, how to make it something that's sort of more realistic and something that in principle you can learn, and something that can cover a lot of different things from moving your finger to, going to the airport or something. And the idea, as probably many of you know, is that you have sort of elemental actions as before, but you also have these sort of aggregates called options that themselves launch a policy that behave for a while and then return to the top level controller, and this can nest, right? And so the idea is, it turns out that if you do all the accounting for this using some tricks from semi-Markov processes and stuff, that everything still kind of works. You just have to sort of keep track of where you are in the hierarchy. You need more than one error signal now. But basically, the TD story works both for learning option policies and for learning top level control policies in the presence of these kind of richer actions. And so I guess the main thing to say is this sort of interesting area to study, and there's various evidence that people do this. But at the core, it's like this basic temporal difference learning or model-based reinforcement learning story we've been talking about basically still works, right? You just have to do a little bit more accounting, but the core mechanism doesn't change. It's just like you have, a bunch of cortex kind of on the output that turns whatever this thing is choosing over into sort of complicated sequences of actions, right? And trades off across levels of the hierarchy. So it's if you do a bunch of work on the output, learning about the action space, this is kind of a theory about how to do that. And then at the middle, you can still have this kind of reinforcement learning we've talked about before. The other thing I would say about this is my sense, reading your literature, and I could be wrong, is that there's basically not a good story about option discovery, or not a clear story in the same sense that there is of other areas of reinforcement learning. There's a lot of kind of heuristics and ideas, but there's not a kind of clear statement, this is what I want to accomplish, and this is how I accomplish it. And so I think conversely, we have basically no idea where this comes from in the brain either. So people are working about these things, but I think this is a relatively open question in human neuroscience, and I think also in computer science, although I don't mean to be judgmental about someone else's field. Encouraging about opportunities. Okay, there's also interesting neural evidence about chunking of sequences of actions, which I think I'll skip. And one other thing I just wanted to flag where people have thought about making the action space in these tasks more realistic is Yael Niv's thesis. So she was interested in the question not just sort of what to do, like which lever to press if you're a rat, but how fast to press it or how fast to run down the runway or something. So it turns out that, I don't know why this sentence got cut off, but a lot of what dopamine does, if you just give an animal cocaine, right, which pumps up dopamine in his head, the most obvious thing that happens is he runs around faster. He does every lever presses faster. He runs on wheels faster. He just becomes more invigorated. Some of you might know that cocaine is kind of a stimulant. This is true for animals too. Why is it that this and this is kind of really this direct and indirect pathway thing, right, of the invigoration or the control of the release or suppression of movement. Why is it that the same chemical in the brain controls what, so it's supposed to control reinforcement learning about what to do and kind of what things are most rewarding and also how vigorously to do it. So Yale has this nice story that basically considers reinforcement learning, again, in a semi-Markov setting over situations where you're choosing not just what to do, but how long to do it for under differential energetic costs. And this leads to sort of interesting predictions, which basically come down to if the world is richer, if rewards are faster, coming more rapidly, you should work faster too, because you can get back to, the opportunity cost of behaving slowly is larger, right? So that's an idea about why dopamine's involved in both these things and how it could accomplish both these effects at once. And it's also an example of, again, trying to enrich the action space to something that's more biologically relevant. And the last one and the most complicated one is the state. So again, I've been acting as though, I show you pictures of, a pink or a blue, set of slot machines, and that's a state and that's Markov and so on. But of course, in general, it's not clear what this thing that's called S should be in the brain, right? In general, so here's a case where an animal is sitting in a chair and all kinds of things are happening in his sensory world, and all we care about is that whether or not the stimulus is on and when it was on. But in fact, even that is complicated because this is on and then it's off. So this is trace conditioning. That is, this is a sort of flash of light, and then nothing happens for a second. And so here, the animal's sensory world is the same as here, but here he's expecting reward to happen and here he's not. And so this is even this simple example, which we started with, is an example in which the state representation that's needed to support what we think what dopamine neurons are clearly doing is richer than the animal's current sensory experience, right? It's something in his head. It's not just something in the world. To say that another way, the state in reinforcement learning to solve realistic problems that animals find themselves in or people involves a bunch of stuff. It involves perceptions, but they have to be kind of filtered because there's lots of perceptions, and there's only a few that are relevant. There's interoceptive sensations like hunger. There's working memory, like stuff happened in the past and when it happened. And so the current perceptual world is both not enough because it's ambiguous like here, but it's also too much because it's full of irrelevant stuff. So the actual state you need to use to make any of this stuff work at all has not, is very far, right, from the animal's kind of raw sensory input. And of course, this is a huge, non-Markovian state and partially observable state and stuff are a huge area in reinforcement learning. And I will just say one thing, which is that I hope this summarizes it. If you can construct a state that is enough but not too much, then you can use your regular reinforcement learning with it. And one version of this is the belief state MDP, right? So Leslie Kabling's idea that, or theorem in a sense, that the states of a partially observable Markov decision process, the posterior distributions over what state you're in, themselves satisfy the Markov property that for an auxiliary MDP is one example, though not the only one, of how you can have a sort of active process that goes from raw sensations and builds a state representation, and gives it to, again, a kind of core reinforcement learning algorithm that works like before, and that chooses actions, right? So just as we talked about kind of having a fancier notion of actions kind of on the output side from RL, if you have a, cortex, visual cortex inferring stuff about the true state of the world on the input side, that can solve a lot of, that can help, again, keep this core mechanism, give it something it can work with. There's a bunch, this is a problem that people have been working on pretty hard now. Again, Yale Niv has a paper recently about dimensional attention. So in a task where, color, pattern, and shape, some of them are relevant sometimes and not other times, and people have to figure out which is which. That's a case where you have to sort of filter the state. There's timing. There's actually this work on extinction that Sam Gershman did, about exactly what situation, under what circumstances you sort of think you're in the same context as before, and when you think maybe in extinction you're in a kind of new world where stimuli don't, cause shocks or stakes anymore like they did before, and how you infer which world you're in, which context you're in. The idea is you have a sort of latent state in your head representing two different states of the world. And so, again, this is a rich area with lots of stuff going on. Just one more thing about it. Coming back to this frontal cortex area. So I talked about ventromedial prefrontal cortex, and that kind of bleeds into a piece of cortex on the base of the brain called orbital frontal cortex that's also broadly involved in reward and value and so on. And there's a recent argument based mostly on lesion studies from Bob Wilson that this is an interesting area because if you lesion it, you get very subtle failures, both behaviorally of learning and also of the behavior of dopamine neurons and stuff, that could be understood pretty well as not a complete failure of learning, but something like state aliasing, that animals become more bound to the physical sensory world for their state representation, and so they confuse two states that should be different, for instance. And that explains a lot of deficits that you see in rat lesions that animals can learn fine, but they have trouble reversing, especially in cerebroversal tasks and so on. I'm not going to go into details. It's an interesting paper if you're interested in it. Bob Wilson, Nature Neuroscience. But it's a suggestion that you have a sort of state representation, specifically for the sort of internally generated aspects of your state, and that if you lose it, you fall back on a kind of more sensory bound kind of representation. Okay, so that's it, I think. So as I started with, I hope I've convinced you that we in reinforcement and in behavioral neuroscience have kind of consumed reinforcement learning and the expertise of all of you in computer science in sort of two ways. One is conceptual, helping us to think about what the problems are and the sort of families of solutions like model-based and model-free or temporal difference methods, the relevant quantities like states and rewards and values and how they work, and try to apply it to understand different kinds of data. And obviously, or maybe I should say this, the experiments are really simple, right? And so for a similar, have to be to make any progress, for a similar reason, the theoretical stuff we're kind of working with is pretty simple too, but we're always trying to, push the envelope there. It's just, it's a challenge, obviously. And if you're interested in this stuff, not to cite myself, but just because I'm the one who gave the talk, I pretty much tracked 3 chapters I wrote recently, so if you want to read about it in more detail, here it is. And also, I've worked with lots of people, students and advisors and so on over the years, on lots of these different ideas and some of the work I showed and understanding other of the work I showed, and these are some of them. Thanks. Sure.
Hello. So I have a question about model-free versus model-based. So you're presenting them as 2 separate systems, and sometimes one system decides on the action, sometimes it's the other systems, and in some situations it's like a combination of the 2. So I was wondering, is there neurological evidence that there are actually these 2 systems in the brain, or could it also potentially be that it's a single system with a parameter perhaps that changing the parameter, the behavioral output becomes more model-free or more model-based?
Yeah, I think that's a great question. I think to some extent the question of what a system is doesn't have a clear definition, right? So, if you have a system that has both systems as subsystems and then weights them and adds them up with the sum, is that one system or 2 systems? But I don't mean to be glib. So the positive evidence that there's really a separation is from this rat lesion data I talked about briefly, that it seems as though they're disjoint structures that have this double, so if you knock one out, you get the other behavior, if you knock the other, you get the other. So that seems like a pretty clear example of a clean separation, at least in this particular task, right? In the human neuroimaging, we've been hard-pressed to see such simple dissociations, I have to say. That might be because the tasks are different, and it might be because in the healthy brain, the systems maybe are better thought of as interacting rather than so separate. And maybe if we started burning holes in people's heads, we would get these kind of associations that are clean also, or maybe not. And then finally, a lot of this other stuff that's going on, like experience replay and so on. I mean, again, the whole point, as I understand it, of DINA and much of the, pedagogical point of the Sutton and Bartow book is that it's all one thing. It's just you're feeding experience into it different ways. And so, there might be sub-modularity related to how you get experience from a model that's simulated or experience from replay into the same value function or something. But I think the idea that there's something shared between them, that they're more common than not, is an important possibility. Thank you.
So you talked a little bit about the difficulty with state representation. And I guess one thing that you didn't quite mention, but I'm curious about, is diffusion-based models for decision-making, where you presumably accumulate evidence, and at some point you have enough evidence to maybe know what state you're in, and then you make a decision. So can you say a little bit about the relationship of that type of model to the things you talked about?
Yeah, that's a good point. Actually, given an hour, I would have put another chunk of the talk in. So there's famous work, just so everyone's on the same page, associated particularly with Michael Shadlin at Columbia, which is a decision-making problem, which is basically perceptual inference. So animals see a noisy stimulus like dots moving left or right, and they've got to accumulate evidence over time as to whether the predominant motion direction is left or right. And they have nice neural activity that seems to ramp up to a threshold, and when the animal reaches significant evidence one way or the other, he makes a choice in it. The underlying theory there, articulated by Gold and Shadlin, is basically the belief state POMDP story. So this test is basically isomorphic to the lion door problem in the cabling paper, is one way to say it. You keep listening at the door until you reach a threshold in the belief space, and when you cross, and this is precisely the way Shadlin thinks about it, that you're maintaining a perceptual, a state variable, right, which is, am I in the state where the dots are left or the dots are right? And the optimal policy, you guys know kind of a theorem that if I can say this right, the optimal policies in that setting are, the optimal value function is piecewise linear and convex, so the policies are thresholds on the belief space. So basically, that story is a special case of the POMDP story. Some people have, Raj Rao has a paper in which so there are recordings of dopamine neurons in these same tasks, and I briefly mentioned, they have sort of slow dynamics where they track changes in value expectation as you figure out in a hard trial or an easy trial, or you know where the dots are going or not. Raj Rao has tried to characterize those responses directly with a kind of Shadlin-like state estimation engine feeding into dopamine neurons that learn the threshold. The policy now is where the threshold goes. So there's a very close relationship. Whether I like the belief state version of this, but of course, there's all kinds of different ways to augment states that aren't just belief states, and it would be hard to tell apart from the kinds of things Shadlin's doing. And I don't want to be too narrow in interpreting it, but that's certainly the story he's telling is that story, for sure. Okay, well, sorry, Andy.
Thanks for that great tutorial. I have a question for you. So you're talking about state and what it could really mean for an animal. And I was just wondering if anybody has considered that the reward signal itself can be considered part of the state. And I'm not aware of people thinking about that, which means the reward signal can immediately influence the policy and the value function, not as a learning signal, but as an informational signal. And I'm curious about that. Rich and I never used the term emotion in our book. We explicitly avoided it, but if you look at theories of emotion, like Rawls's theory, he talks about emotion as responses to reward signals. And so I think it's interesting to think of the reward signal not, in a dual role.
Right.
And I'm wondering if you know of anybody who has pursued that line of thinking.
So I'm not sure. Well, let's see. So there is work, the same kind of family of behavioral psychologists who are interested in goal-directed habitual behavior and lesions, having specific effects, have been interested in what they refer to as the sensory properties of a reward versus its hedonic properties or something. So there are neural dissociations, arguably, between some kind of signaling properties related to the sensory aspects of a reward, which you might think is state-like or sensation-like, and the more reward-like aspects per se. So that's one thing. I'm trying to think, I can't actually remember what the tasks they're using are, whether they're of any interest to us, but we've also thought about, I mean, a lot of the work that Peter, Dan, and Yelniv and I did on these motivational change experiments where you take a reward and you reduce its, you make it poisonous or something. One way to think of that is that, actually it's sort of written here, right? You can think of the reward as being a sort of a function of the state, right? Like really a function, like it's a mapping from states to a hedonic value. And part of what's going on as your motivation changes is that weighting, that mapping is changing. And in the POMDP case also, the example of this, if I can find it, the monkey waiting for reward, right? And that doesn't get it. Sorry, just ran through all my things. The reward not coming, or the reward coming, is a signal of a state change, right? So if I'm sitting there kind of waiting for the state to change, there's a sensory event which is a function of a latent state, and if it happens, it's both a reward and a signal, right? If it doesn't happen, then there still might have been a signal change. So that's one kind of somewhat trivial example where a reward event is also a sensory event that matters. But you may have something more interesting in mind. I'm not sure.
Not at the moment.
Okay.
Yeah, thanks.
Sure. All right. Thanks a lot.